But I think I just want to it's a small class, only 4 of you. We just talk to each other, okay, communicate, and let me help you. I hope this hour and 15 minutes is not, it's very useful for you. Hey, Dylan. Hey, just keep your camera on. Okay, let's communicate. Just talk to the other guys. It's a small class today. I want you to really get some benefit from communicate with me today. Okay, so let me share my screen. Okay, let me give you a quick overview for those contents. Okay, for the whole semester. I don't know, you're supposed to be already started preparing, so you already know what you expect to see in the what are the material we cover in the class. But let me give you an overview. Okay, so okay, hold on, I have a problem with my pen. Okay, let's select the color. Okay, start from chapter 2, right? Chapter 1, you have nothing in chapter 1, so it's an introduction. Chapter 2 has a little bit material, possibly be covered. Okay, maybe I won't give you a standalone problem for chapter 2, but maybe some of the material would be incorporated in some of the comprehensive problems. I think there are 2 contents, only 2. You know, what are these contents? Remember?
Was that surface tension chapter?
Yeah.
Oh no, viscosity?
Yeah, viscosity, that's the first testing point. It could be the testing point, right? We introduce one equation. I just want to write down all the equations you need to memorize. Okay, for the hold on, there's some people in the waiting room. Okay, if you join late, let's turn on your camera. We look at each other and let's communicate. Okay, any question, please jump in. I start with some overview of the content. So I think that's the first equation. Shear stress equals to viscosity d velocity dy, right? It's definition. That's the definition for the shear stress. I'm sorry, that's definition for the viscosity. Usually people know shear stress is proportional to the velocity gradient, which is the strain rate. So they are related, but there must be a coefficient, right? So viscosity is that coefficient. This is a beautiful equation. It tells you totally the fluid dynamics. Okay, cause and effect. Okay, if you think the shear stress is the force per area, so it's a cause, right? If you apply shear stress to the fluid, the flow will move. Okay, it gives you a velocity gradient. Okay, so see, that's the cause and effect. We talk about the dynamics, right? Dynamics is the subject. We study the cause and effect. Okay, motion is the effect, and the force is the cause. Okay, or the vice versa. You can say, hey, there's a motion. As a result, you generate forces. Okay, so they are related. So viscosity is the unique fluid property. Okay, to relate the force and the deformation of the fluid. Strain rate basically is the deformation of the fluid, right? So that's the first equation. I think the conceptual wise, you probably need to fully understand this equation, right? This is really the cause and effect. Okay, then surface tension, force per length. Okay, we did many examples for surface tension, or do the experiment for surface tension, most of you, and shear stress. Okay, also shear stress and the strain rate. These are the 2 topics possible in chapter 2. Okay, so I guess this is the 2 equations probably you need to remember. F over L, okay, in case bear with my writing. Let me use a capital letter L, F over L. Okay, that's surface tension. Chapter 3. Chapter 3 is really important. It's a big chapter, include everything in hydrostatics. Okay, chapter 3, you really need to pay attention. Okay, there's many contents in there. That's basically half of the mechanics, right? Usually in solid mechanics, you have one semester for statics, one semester for dynamics. Okay, in this semester, we kind of also like a little bit less than half of the semester, we work with statics. Okay, so couple points, you know, they're the Pascal's law, right? Remember Pascal's law? It's a hydraulic machine. Okay, so small area, large area, they have the same added pressure. Okay, if you have a larger area, then you feel bigger force. Okay, if you have small area, you have a small force. But it's because of the added pressure to the fluid system, that added the delta P, you will feel okay, everywhere inside the fluid system. Okay, so if you have a big area, okay, then you actually pressure times area become a bigger force. That's the principle of hydraulic machine. Okay, we had classic examples, remember? I have homework problems, but I do have one example, hydraulic jet, right? To push to make force. Okay, so Pascal's law is, what is the equation? Equation is easy, just delta P is equals to delta P. The added pressure is the same everywhere. So that basically, that's the equation, not much of the equation. But I think really the equation is force equal to pressure times area. That matters. Okay, you have added pressure. You have to have an area to convert the pressure into force. Does that make sense, everybody? Okay, one important concept in this class is the conversion between the pressure and the force. Eventually, what's the result you see is from the force. What's outcome, what you feel is from the force. Okay, but we talk about the pressure a lot here. In all the equations are pressure. So pressure can be converted into force. P times area is the force. So in Pascal's law, basically that's the key. You know, you have the same amount of pressure, but you have a bigger force. You basically receive bigger force. If you have a bigger area, bigger area, then for the added pressure, you will feel bigger force. If you have a small area, then a small force. Okay. Then is the hydrostatic principle, point pressure. Point pressure calculation. Okay, point pressure, you need to know, okay, seriously, that's the basic. If you don't know, then it's really have trouble doing any of the exam. Point pressure, any point inside the fluid, you should be able to calculate the pressure. If it's hydrostatic, then it's really simple. Okay, so basically the principle is, okay, P plus gamma Z is equals to a constant, or P over gamma plus Z equals to a constant. Okay, you write this form, but in that when you solve the equation, you're not using any C, right? You usually compare 2 points. Okay, 2 points to calculate the pressure. P1 plus gamma Z1 equals P2 plus gamma Z2. Hopefully, you know the reference point. You know the information on that reference point. Then you can find the pressure or the elevation for another point. Okay. Does that make sense? This is a review, but I think that at this moment, you should be already familiar with those things. Okay, we did a lot of quiz, did a lot of homework problem, class, example problems. Okay, so this is the fundamental. Okay, you should know how to calculate pressure inside a stationary fluid. Okay, and also we have a shortcut alternative method. Do you remember? If you have a multiple fluid in the tube, okay, we start from 1 point, P2 equals to P1, then plus minus what? Gamma H, right? Okay, then plus minus how many portions? Okay, I want you to review that too. This is a very how to say, it's a smart way to solve problem. If you use the original method, if you have a multiple fluid, it will become more tedious, more steps. And this is the one equation that can lead you to the final answer, even you have 10 fluids inside your device. Okay, this is the alternative method, but it's a smart method. Sometimes you need that. Okay, if you multiple fluid in the hydrostatic region. Okay, so I give you directions. You just how you prepare. Okay, go back. These are the content testing points. Okay, you have all the resources. You have all the videos. Okay, all the quizzes, homework problems. Going through your resources to find an example to fully understand, to practice those contents I listed here. Okay, if you fully understand all the contents I listed today, you should be good. Okay, you should be good. And that's the goal of the class, actually, eventually, is to understand these important contents. Okay, any question, please jump in. Any question here, concept-wise. Okay, so what's the next one? Plane force. Plane force calculation. Okay, plane force calculation, that's also one of the important points we made in the class. Two calculation, one is the force. Okay, you have two equations. One is the force, one is YCP. You have two equations, right? Or YCP minus Y bar, okay? So that's the equation, okay? These two equations you need to memorize, okay? The force equation is simple. It's just the pressure on the centroid of the surface times the area, okay? I think everybody can remember that, right? Can you, at least all of you attend to this class? Okay, so remember that, that's piece of cake. Basically, you find out the pressure on the centroid of your surface. So how to find the pressure on the centroid of the surface? That's here. Number two, you need to know, okay? Find the pressure in any given fluid, any given stationary fluid. So your knowledge build it on based on the previous knowledge, okay? That makes sense? Okay, so find the pressure on the central location. So identify the central location. Okay, and find the pressure on it. Okay, most of the time it's just gamma times the water depth sitting on top of the central location. Okay, and Y bar YCP, you probably need to memorize that equation. That's the only equation. I think it's a little bit difficult to memorize, but go ahead and memorize it. I won't give you that equation, but I will give you I, the equation for the moment of inertia. Okay, in that equation, there's I, right? Y bar I, okay, area, okay. Everything you can find about Y bar A, no problem, but I, you need to, I will give it to you, okay? Don't worry about the I. And I will give you that diagram in the appendix 8.1, so you should know where is the central location also, okay? If you don't know, okay, I assume you know. Also, the area of that the surface, I will give it to you too. So basically, area equation is there. If I give you a like a surface like an optical shape or something, elliptical shape, then I give you the equation for calculating the area. Okay, for square, for circle, you need to remember, right? It's so easy. But I probably will still give it to the area equation. Okay. So this is another topic. So it could be comprehensive problem in this topic, plane force. Remember all the problem we went through in the class? Okay, seems like a kind of complicated static problem. You really need to know how to draw free body diagrams to solve this problem. Okay, this type of problem. Okay, FBD. Again, I want to write one more time here. Okay, we practice a lot, and that's the focus of my class. Also, one of the focuses to make you know how to draw free body diagram correctly. It has to be correctly. You can't stand any error in the free body diagram. If you have any error in the free body diagram, everything after the free body diagram will be wrong. Okay, your equation is based on the free body diagram. This is the engineering way. If I just want to convey this idea in this class, that's the engineering way. Okay, free body diagram 100% correct. Then you can list your equation 100% correct. Then you can solve the problem 100% correct. Okay, if the starting point is wrong, then there's no hope then. Okay. What's the number 4 knowledge contents you needed in the chapter 3? Buoyancy. Okay, buoyancy could be a typical static problem. FBD, again, free body diagram. Write it down. Put the buoyancy always upward. Okay, as an arrow. Okay, place all the forces possible in the problem. Okay, then write down the force balance. Okay, sometimes you need a moment balance. Okay, if there's a rotation involved, okay, in your problem, your first choice maybe think about try to use moment balance equation, summation of moment equal to 0. Okay, you need to know a pivot point, write down the moment equation. Okay, again, the free body diagram has to be correct. Okay, if it's not, then no hope. Okay, that's why a lot of students score really low in the dynamic class, static class. Okay, because if your starting point is not right, then it's a problem. Okay, I extremely want to focus on the free body diagram on those static problems. Okay, but for content one, buoyancy not much. Basically, it's just a force, right? It's just a force and always go up. Okay, and the force buoyancy equals to gamma of the fluid. Gamma of the fluid times the volume submerged. Be careful, there are some conditions for these two letters. Okay, gamma is not the gamma of the material. If you calculate the weight, I want you to remember the two equations together. If you want to calculate the weight of the object, which you always use to balance the buoyancy force, is the gamma of the object times the volume of the total volume of the object. I said OBJ, object. Okay. Be careful. We can't tolerate any mistake as an engineer. Eventually, you'll become a career engineer. Then humans' life rely on you. We can't make any slightly mistake. Okay, that's why you get paid the big bucks for not making mistake. Okay, be careful. Start from be a student. You start to practice that and try to create the habit. My goal here is all my calculation, everything I write down, 100% correct. Okay, very, very important. I want to train you to be a good engineer. Okay, not just passing the class. So weight, remember this equation. You probably need the weight. Professor. Yes, Stalin.
I see you have, that's gamma OBJ times V. Is that GG?
Also OBJ, object.
Oh, okay.
Okay, I'm talking about those equations. Yeah, bear with my writing. Okay, yeah, thank you for asking. Remember these two equations all together, so memorize it. Okay, that's important. Easy for you to do the calculation. Sometimes gamma object times volume of object, it's easy to memorize. Then you can also do mg. Okay, but in some the trick is in our problem always the volume sometimes is given, gamma it's given, rho g is already given. Why not just use that equation? Mg is okay, but still m is rho times volume, right? Then times g, same, basically they are the same thing. Okay, so remember, because if you remember these two equations together, it's easy because both of them are gamma times volume. Okay, just different gamma, different volumes. Okay, just be careful. For the weight is the object's gamma and the total volume of the object. But in the buoyancy is the gamma of the fluid. Okay, buoyancy is a property, kind of like a property of the fluid. So it's gamma of fluid times the volume submerged, only submerged. Be careful, it's not the total volume. Sometimes you need to know how to separate the volume into submerged part and the non-submerged part. Okay, so but to solve a problem, hey, this is just we just introduced basically a very simple equation for buoyancy. But when you solve a problem, it's following the static principle. So following the principle of solving static problem, which is free body diagram, equation, force balance, or moment balance. Okay, that's what I want to emphasize in today's review. Now, next, that's it for chapter 3. Although it's a bigger chapter, but there's only, to me, is only 4 testing points here. Okay, I just want to include everything in this semester in today's lecture, 20 minutes maybe. Okay. Any questions so far? So not many equations to memorize, right? That's why I don't want to give an equation sheet, because there's really not many to memorize. You be an engineer, you need to memorize something. Okay. I think the only equation you're not familiar with to you probably is that YCP equation. Go memorize it. Okay. The rest of the equation is so super easy. Okay, so the alternative equation, right? Go up and go down, go up minus, go down plus. Just remember the sign, plus minus. I said here. Okay, the gamma times the level, right? Times the water level, the fluid level. Okay, so that's chapter 3. Chapter 4. Chapter 4 we start the hydrodynamics, right? Basically, chapter 4 is to describe the flow. That's the first lesson before you can calculate the force, right? So describe the velocity first. So I guess the first testing point is velocity and the acceleration. Both are vectors, okay? Velocity and velocity, not much. Basically, you have to understand the vector field. Velocity vector, you have u, but all can be x, y, z, and t, okay? I, j, v component, w component, k. So it's a vector. So follow vector operations. U, v, w are all possible function x, y, z, t, right? V is also, w is also this. If I ask you, hey, if there's a place that the velocity equal to 0, what do I mean? Velocity equal to 0 means all 3 of them, the components equals 0, okay? It's a vector. So getting familiar with the vector, the fundamental meaning, the concept of vector, okay, and how to calculate the vector, how to do the vector operation, okay? That makes sense, everybody? Okay, basically you treated the velocity just like a force. So you have 3 components. Force is Fx, Fy, Fz. Velocity also has 3 components, u, v, w. Okay, treat them separately, calculate them separately. Then you can find out a velocity magnitude, which is what? Velocity, let's say velocity and magnitude equals to u squared plus v squared plus w squared. That's it, right? Okay. Euler's equation. Okay, we have examples in the lecture about Euler equations. Okay, how to solve problem. I think I gave 2 examples on Euler's equation. Okay, Euler equation is to convert acceleration into pressure. Okay, now you have the motion. You describe the motion, you use acceleration. Okay, so directly from acceleration, you can calculate the pressure. Basically, that's the purpose for the Euler equation. Okay, but this is the different. Euler equation is bad. It's a differential equation. Okay, Euler equation is bad. Differential equation. So if you want to solve a problem, use Euler equation, you have to do integration. You have to solve that differential equation. Okay, so there's plenty of example and homework problem we talk about Euler's equation. Please look into that. Okay, how do we solve Euler equation problem? You need to do an integration basically to solve it. That makes sense? Okay, but your goal is to get pressure. Okay, if you get pressure, then force. Okay, that's always our goal as an engineer. You know, in the dynamics here, you're just dealing with motion and the force. Motion and the force, motion and the force. Find the relation between motion and the force. That's it. Okay. Number 3 is Bernoulli. Of course, Bernoulli will be more easier from velocity to pressure. Okay. Velocity pure field, it's much easier to measure. Okay, so that's why we use Bernoulli way more than the Euler equation, right? Euler equation is from the acceleration. So from when you see a problem, you know, if you want to decide it's Euler equation or Bernoulli equation, then they just look at the problem statement. Is the acceleration given? If the acceleration is not given, the velocity is given, then definitely it should go to the Bernoulli. Okay, so when you read the problem statement, I know everybody under pressure in the test, you know, when you're reading this, the problem statement, you feel bad, you know, I know that, I was a student, right? But the easy way is when you look at the problem, read the problem, what you think is which equation I'm going to use to solve this problem. That's why I designed those experiments, ask you to do the small experiments. In reality, there's a problem statement, you use an equation basically to characterize it. Okay, then you can design experiment to do that. Same thing, when you read the problem statement, you think which equation I'm going to use. Okay, you don't have many choices here. Okay, so how many equations? Not many. It's very easy to pick an equation immediately after you read the problem statement. Okay, is it hydrodynamics or hydrostatic? Hydrostatic, I only have that many equations. 4 items here. If it's hydrodynamics, chapter 4 and 5 and 6 and 7, maybe. These are the equations. Each chapter has one equation, basically. 4 has 2, basically, right? That's it for chapter 4, Bernoulli. And okay, you need to remember those Bernoulli equation and Euler equation, right? So simple Bernoulli equation, everybody remembers, I guess. And how to apply it? Finding 2 points. Same way you apply the hydrostatics, okay? Chapter 5. Conservation mass equation, just one equation. Okay, maybe you can put the summation. If you have multiple in and out. Well, chapter 5, you know, it's very easy to incorporate in any comprehensive problems. Okay, so basically it says it's just the, if it's a steady state problem, then the mass flow rate in equal to mass flow rate out. Basically, that's how we calculate the velocity many times. Remember, if you did practice any of the homework problems in later chapters, conservation mass is always being used as a flow rate is same. You know, if it's a steady state, then this term is gone, then become mass flow rate in equals to mass flow rate out. Density is the same, basically just the Q in equal to Q out. We use this to calculate the velocities, okay, in the future chapters, right? In comprehensive problems, sometimes even chapter 4's problem, Bernoulli's, right? You need a velocity, okay. Okay, but for the flow rate, it's possible keep in mind this. The 2 ways to calculate the flow rates. One is if the velocity is uniform, easy. But if the velocity is non-uniform, you need to do the integration. Okay, that's 2 ways. That's a decision you need to make before you do the calculation for flow rates. Flow rate you need it for many problems, not only the conservation mass problem, momentum problem, okay, energy problem, all the problems you need a flow rate calculation. So if possible, I give you a non-uniform velocity field. So you need to do the integration. So I think I assigned homework problems for many different surfaces, okay, to calculate the non-uniform flow rates. Okay, look at how to do those integration dA for different shapes. Okay, so that's something you need to know too. But if it's a uniform velocity, then it's easier. We often see problems to calculate the velocity based on flow rate equal. Flow rate in equal to flow rate out. Quiz, we have quiz, right? Many quizzes is that, right? Okay, so that's only one equation for chapter 5.
What does that say?
Yeah.
What is the on the left side of that equal sign? What does that say? D whatever, D what?
Seems like you haven't prepared. Okay.
DMDT?
EMDT, yes. Total mass conservation, the change of mass, total mass in the
Okay.
control volume.
Yeah.
Right?
I don't know if there was a D or a T or what.
Time, D over dt, D mass total capital. Okay, this is not supposed to be the first time you hear this.
Oh, wow.
Yeah, you need to spend more time in the next 2 days. Okay.
That's
Yeah, it's not.
mass.
I just didn't know if we're talking about the momentum equation with the velocities and you just didn't write them or what. I didn't know exactly what you were trying to put together there.
What did you say? I'm sorry, I didn't hear the beginning of your sentence.
It's not that it's the first time I've seen it. I just didn't know if this was the momentum velocity. I mean, the momentum equation with the velocities, and you just
No,
didn't
it's not.
put
It's
them,
not momentum
like, that's part
equation.
of
This is the conservation mass. We are in
mass
chapter
flow
5.
rate.
This is the conservation of mass. Okay, you know, this is a concept for the whole chapter 5. It's just this equation.
That DMDT only applies when there's like a vessel collecting.
You have a control volume. Okay, you have a, for example, tank. We see tank problem a lot, right, in chapter 5. So that's the total volume you're interested. So the total mass in that tank, how does it change? Okay, that dm over dt means that the change of the total mass in your container or in your pipe or in a volume that you're interested. Okay, so that's the total mass change, the rate of mass change in terms of time. Okay, do you remember those examples how we did in the class? The tank, emptying the tank, how long it would take for the water level to drop, right? So that tank is your volume of interest. Okay, so the mass changes every second inside that tank. That's what dm over dt means. Okay, this is really Cal 1, guys. Okay. So that's what I try to say is for those conservation laws in fluid mechanics, you need to have a target container you're interested. Okay, you have to have a target. It's not just, you're not looking at the fluid, you're looking at a container. How the mass changes in the container or in the pipe. Okay, do you see my point? Conceptually, it's not really the fluid. The fluid is just past it. It's gone forever. I don't track it. Okay, but I track my space, my volume, my interested container. Okay, so that's it for chapter 5. Conceptual-wise, that's only one equation. Chapter 6, also only one equations, conservation of momentum. We only talk about the steady state conservation of momentum. I simplify, I just reduce a lot of content in chapter 6. Only equation I want you to memorize is the summation of force of your system in your control volume, okay, is momentum out minus momentum in. Okay, you can put the summation there too. Okay, if you haven't memorized the procedure we solve problem, you really need to look at we have 2 examples in the lectures. I think I would strongly recommend you to watch all those lecture video again before the final exam. Really, seriously, all the video again, okay, for each content. That's the only way. If I give you a conservation of momentum problem, that's the only way you solve it, is to have the free body diagram and the momentum diagram, draw the diagram, then put the equal sign, write the summation force and the summation of momentum out and the momentum in. Okay, expand these equations, then you can calculate one unknown.
That's one where you put X, Y, Z.
That's right,
First.
it's vector. Momentum is vector. Force, you see, force equals to momentum. Both of them are vector. So you have X, Y, Z direction. Look at that example. We have two examples. One is a 1D problem. One is 3D problem. Okay.
I got a question.
Yeah. Go ahead.
Go ahead, Josh.
Momentum is just mass times volume.
Oh no, it's mass flow rate times velocity. All right, guys.
That's what MV. Yeah, that's what I.
Yeah, I usually put the V like this as volume. Okay, put the V like this as velocity. Okay. So let's have different meanings. Okay. Velocity, momentum. Okay, it deals with the velocity. Mass flow rate times velocity. Okay. Again,
I had a question about this.
Yeah, Patrick.
So I was doing some problems last night and I was getting a little confusion with the negative sign. So when you're doing the right side, do you determine a negative or positive for the mass flow rate and the velocity, and the mass flow rate is out is positive and
I'm
is
sorry,
negative?
this is the type. I can answer your question. Yeah, here. The whole thing. This is a momentum. Oh, my momentum is not mass flow rate. Okay, so momentum as a whole is a vector, has direction. Don't just look at the mass flow rate or velocity direction. Okay, momentum as a whole direction. When you draw on the momentum diagram, you put an arrow, right? Is that right? The arrow represents the momentum, so it's an arrow. Okay, look at that arrow direction to decide each term is positive or negative.
Yeah, that's what I was doing at first, but some of the problems were like if I did it like this with neglecting the direct, like
no, you did it wrong.
Whether V was in positive X or negative X, they were putting.
Okay, let me give you an example, a drawing here. Okay. Again, follow me. I give you instruction is 100% right. If you follow it, you will score 100% on the test. Okay, follow what I say. Don't think about velocity. If you have a momentum, you draw an arrow. Is that right? Okay, this arrow represents the momentum on the momentum diagram. Okay, you have another momentum going out like this. This is the momentum. Not thinking about this is the velocity, momentum. You draw momentum diagram. You don't draw velocity. You follow me? Okay. So for this momentum, that's the expression m dot v whatever. Okay. This momentum has a direction. If you want to look at the x direction, this momentum is positive. If you look at the y direction, this momentum is negative. Okay. This momentum is negative. So when you calculate the mass flow rate times velocity, you already have the value. Okay, don't use sign, I'm sorry. Don't use sign, just put the value there. After you calculate the value, put a sign in front of it. Okay.
That's what I'm saying. What do you use to say that the momentum is negative if it's going out and you put out minus in?
Because this is the y direction. This momentum is negative. This sign is the equation. It's not the direction. This minus sign is the equation. Okay. You need to leave the minus sign here. Okay. But the term here, each could be positive or negative based on the direction in your coordinate system. Okay. And the easy way not to make a mistake is to calculate the magnitude first. Momentum magnitude basically is mass flow rate times whatever velocity you have. Don't use the sign in this for when you calculate the magnitude. After you calculate the magnitude, put a sign in front of it to decide what the direction. How about that? That will make it a little bit easier, right? Okay. If it's positive momentum, it's positive. If it's negative momentum, it's negative sign in front of it. Okay. Do the magnitude first, then place the sign. Okay, so each term could be positive or negative based on the sign. Then this negative sign has to be there. This is from the equation. That negative sign doesn't tell you any direction. It's just the equation. Right, Patrick? Did that make sense to you? I think that's a good question. I think it's help everybody's right. Everybody here, make sure it's clear, crystal clear.
That was a good question, Patrick. Thanks.
Yeah. This is the confusion. So when I was a student, when I do this, I always confused because, hey, what is the velocity direction? Whatever. Don't think like that. Just think momentum as a whole. calculate the magnitude of momentum, then decide the direction.
So,
Okay.
Professor, let me get this straight. So basically, whatever you're given in the direction for the momentum, that's what's going to dictate with positive or negative in the
That's
XY
right.
direction.
That's right. That's why the
Okay.
drawing here is called a momentum diagram. So the arrow represents the momentum direction. Basically, it is a flow direction, sure. But when you think about, do the calculation, think this is the momentum the arrow represents.
And that only qualifies for momentum. That doesn't qualify for anything else when you calculate.
This is the momentum. Just like I said, this arrow on the MD, the moment diagram, represent the momentum
I
only, not the velocity. Okay, don't think it as velocity. It will confuse you. Okay, just treat it as momentum.
So it really
It's
the only
beneficial. Yeah, Josh.
really the only example we did on this was that pipe hanging from hangers or whatever.
We have
And it
two
only-
examples. 1D is the flange with the 1D pipe. The other is the 3D. It's a bend. Okay, so you have 3 dimensions. So they have two examples.
Yeah, that's the last one we did.
Yeah, so
We didn't actually have, I mean, we had a Z, but it didn't change in the Z direction. You know,
if there's no momentum in Z direction, it's just the force balance in the hydrostatic in the Z direction, right? Because there's no flow, no momentum along Z direction. The fluid is not moving along Z direction. So you don't have a momentum. Okay, so momentum equal to 0. So summation force, it's just equal to 0 on the Z direction.
okay, I guess what I'm getting at is, should we go find some problems that do change in the Z direction, so that we're more familiar with putting it all together?
But what is the difference between this? It's separate. The Z direction is separate with Y direction and X direction. You know, if you know X direction and Y direction, it's the same way you do the Z direction, right? They're not related, basically, what I tried to say. It's a separate, in the vector world, the components are separated. Okay, so, well, to me, of course, you can looking for some 3D problems in the textbook, homework problem. I don't know. I don't remember I assigned a problem with 3D. Maybe I did. Okay, but to me, what's the difference? 1D is enough to do the problem, because you know, you look at the X direction, all the momentum, all the forces. Then 2D Y direction, X and Y. That 3D problem, basically X, Y, and Z. But in the third dimension, basically, it doesn't have momentum. Okay, so it's easier for the calculation. But if it does, you put the momentum out minus momentum in Z direction. That's it. I don't see difference, basically. I try to say. Do you agree?
Well, yeah, I'm just saying, like, say if that pipe was curved the same way and also down, will we need to draw another diagram? Will we need to draw it?
You don't need to draw the diagram. But 3D, it's basically difficult for you to draw. That's why I feel it's limited on the 3D application on the homework.
I'm talking about like a different plane. Like we draw that XY plane, where we need to draw the XZ plane. So we can kind of
see usually what I do is I do this. The direction is go out of the paper. I go this. That means that the arrow is going into the paper. Okay, so you can still do the momentum diagram by doing this. So if there's a momentum going out, you can draw an arrow like this. If there's a momentum going to the paper, then become like this. So it's just a way of draw it. It's difficult to draw in 3D, third dimension. The paper is only 2D, right? You see my point?
Yeah.
Is that what you guys?
Which direction do you?
Yeah.
I have a question.
Which direction do you typically pick to be the positive Z?
Gravity is negative Z.
Oh, that's if you're looking at it from like an aerial view.
Well, I don't know if I get your question, but usually, physically, you have to have a positive direction and a negative direction, right? Z is easy because gravity is always negative direction. So the other direction is positive Z. But how you want to draw it, it's up to you. You want to go out of the paper as positive or go into the paper as positive, it's up to you. But you need to know physically, in reality, the gravity is negative Z, basically. Right? Does that make sense, actually?
Yeah, I guess that just depends on which way you're looking at. Like if you're looking at the pipe from an aerial view, then into the page would be negative.
Yeah, yeah.
But if you're looking at it like from the side, then your into and out of the page wouldn't have anything to do with gravity.
This is just you just need to remember gravity is negative z basically. Okay.
Okay.
It's up to you how to really up to you how to draw it for you to fully understand, for you to clearly show. But then gravity is in negative z. Okay.
Gravity needs to have the opposite sign as weight.
Weight is gravity is not the opposite sign of the weight. Gravity is the direction of the weight, right?
Oh wait, no, yeah, normal force. Never.
Okay. Again, no mistake on any small tiny things. That's the difficult part to be an engineer. Okay. No mistake on anything, any slight little thing. Everything has to be perfect. Okay. This is chapter 5, chapter 6. Oh no, this is already chapter 6, right? Yeah, this is chapter 6. I guess each chapter has one equation. Chapter 7, you have a chapter 7 and a 10. Okay, chapter 7 has the equation. That's just the Bernoulli equation. P1 over gamma plus C1 plus V1 square over 2G plus, it's a complete equation, right? You have the pump head. This is the system equation between 2 points in the system. Within these 2 points, if there's a pump, if there's a turbine, if there's a loss, everything will be considered. This is the universal equation eventually. I guess industry people call it the Bernoulli equation, but it's actually a system, energy system equation. Okay. Memorize it. That's really no difficult to memorize, right? Bernoulli equation, you're supposed to remember Bernoulli. Okay, then only additional 3 term is the pump, turbine, and the loss. Okay, now that's it. Equation was just solving problems. That equation can help you calculate one unknown, right? You have to know everything else, depend on which is your unknown from the problem statement. But when you read the problem statement, you should immediately be able to write down the clear equation. If it's energy equation like this, if the problem is using energy equation, write it down. Okay, then you can have something to look at. Okay, to see which is the unknown in the equation. Can you solve it by knowing everything else? Okay, did you see the point here? Okay, that's a procedure. To me, I feel it's pretty straightforward. But basically, pick the equation. That's eventually it's extremely important. Pick the correct equation. Write it down. From looking at it, let the equation tell you what's the next step. Okay, what do I need to calculate from this equation? Do I have everything else, okay, in the equation other than the unknown? Chapter 10. Chapter 10 is about the loss, okay? So we can model the loss, frictional loss, minor losses, okay? That's it. That's all the equations this semester. Can you memorize those? I think it's less than 10, right? I think really less than 10 equations, maybe 6, 7 equations you really need to memorize. Some of the just common sense equations everybody knows. Okay. So chapter 10 is very applied. This basically will be used with chapter 7, okay? Use the with chapter 7, okay? These two, the problem always together. Right, does that make sense, guys? Just this equation. These are the model. Combine these two are HL, okay? HL is the summation of the frictional loss and the minor losses. Then this is very practical applied knowledge here. You need to find F and the K from engineering handbooks. F is from Moody diagram. K is really a list. Okay, a table. You need to pick the correct case. Okay.
I think you pointed it at turbine head, but I
No,
understand
it's just I pointed to the whole equation. Whole equation is in the box. I just said these two are related. Okay, usually a problem always combine these two chapters together. Okay, because the turbine head and the pump head is nothing to model. Basically, is the spec, manufacturer spec, right? Specs. If you buy a pump, buy a turbine, these are the specs from the company. But the loss really differs from different situations, from the pipe lengths, velocities, from those fittings, okay, from those fittings, and that really can have a lot of variations there. So you probably need to know how to calculate that. That really I need to know this, because if you pass my class and come back to working in a company there, you don't know how to do this, that look bad on me. They know me, most of the people in a lot of managers in the companies. Okay, my student need to do the piping calculation, need to do those energy calculation. Okay, so bottom line is this. Any question before I move on to some problems?
So these are the equations, but what about constants we should know? Are you going to give all us the constants?
I give some properties like viscosity, those kind of things. I will give it to you. I don't expect you to memorize it, but you have to memorize something common, like a density of water, 1,000 kilogram per meter. Okay, density of air, okay, 1.2 or something like that, right? Everybody use. So gamma of water, 9,800. Okay, gamma of air, 9.8. Okay, or 10. Okay, so those common values in English unit or in SI unit. In English unit, the gamma water is 62.4. Okay, this thing is really benefiting you, okay, as a future engineer. You need to memorize those common properties. Okay.
That was going to be my next request. Can we just use the metric system and not mess with the English system?
Hey, come on, you're working here. You need to know English system. Come on, you're in America, right?
Yes, please.
Yeah, you know, I honest with you, I like the metric system. I like the SI system too, but I was forced to learn the English system because
I mean, it's a lot more intuitive. The English system just doesn't make a lot of sense. So it's hard to follow through stuff.
But see, I'm trying to.
It starts turning into slugs and all the dynes and all this other stuff.
Yeah, I know. I fully understand this. But if I don't teach English system, the local engineer will be mad at McNeese at our program, because that's what they use every day in their plant. So we really need to have
it wouldn't be the first time.
That's fine. I usually, if we have a 4 problem, for example, if we have 4 problem, probably likely maybe all 4 of them will be a metric system. That's possible, but maybe there's one of them will be English system, something like that. So that's always my when I give problems, you know, I give more problems with SI system, less problem with English system. How about that?
So you said we have 4 problems. That's how that's good.
Yeah, I changed my mind. I feel you probably 5 problems is too much for you. Okay, so in 2 hours I just tried to give you a little bit easier. 4 problems, but yeah, total 4 problems for 2 hours. Okay, I haven't finalized my exam yet. I don't want to do it before today's lecture, so otherwise I might leak some information to you. So I will work on the final exam after today's meeting. Okay, so I will give but I decided to give you 2 problems instead of 5. Okay. Oh, I'm sorry, they'll give you 4 problems instead of 5. And 4 problem could be, some problem could be more difficult than the others. So the point distribution might not be 25 each. Okay, it could be, some problem could be 30 points, some problem could be 20 points, something like that. So it's not like a similar difficulty. Okay. Any other questions? Any questions I can entertain?
So on a project, I see you told us that we can use from chapter 5 and beyond.
Yeah, on the chapter 5, 6, 7, 10, I guess it's all okay.
Right.
But some chapter is difficult to do experiment. Some chapter is easier.
Exactly,
So,
and that's the point I wanted to make. because it seemed like a lot of the applications that you would need to use to apply these equations require like certain instruments that only a lab would have.
Yeah,
So
no,
it's
no, no.
like
I'll always, Dylan, I always say this. Okay, if you follow my lecture on the experiment, if you follow the lecture, if you watch the lecture, you will know. You always find a way. You always can find a way to not using complicated instruments to do your experiment. For example, I just want to reiterate here. For example, you have your experiment will use Bernoulli, although this is chapter later, it's probably not Bernoulli, but let me give you the example. So when you design an experiment, you need to decide that equation first. Okay, I'm gonna use this equation for my experiment. My experiment gonna verify this equation. So if I decide I use Bernoulli equation, write down the equation, I will see, okay, this is my Bernoulli equation. For example, just like this, I don't want to give you an example in chapter 5, 6, 7, and 10. This is chapter 4, okay, for example. So you look at this, you're measuring every turns, okay? Maybe you know some of the turns, so you don't have to measure every turns, okay? So for example, what's more difficult to measure? Here, you have pressure measurement, elevation measurement, velocity measurement, okay? This is also pressure, elevation, velocity. Which one is easiest to measure? Which one is more difficult to measure? If you need some need instrument, some doesn't need instrument, right? Which one require more instrument to measure?
Pressure.
Pressure, this is the most difficult one. Okay, I need an instrument. I don't want to buy an instrument. Okay, so what you do? You design it. You design your experiment. Let's say, hey, let me put my experiment two ends of my fluid, both of them exposed to atmosphere. Okay. If they're exposed to atmosphere, I know they are zero, so I know the value. I don't need to measure that. In order, I can measure the height. I can design an experiment to say, hey, how high it will go. Can you measure the height? Well, come on, everybody can, right? You can have a ruler, right? Or you think it's too non-challenging, too easy. I measure velocity. I get the height measurement, okay, easily by ruler, okay, by tape, okay. I can also measure velocity. Velocity is not as easy as the height, but it's not really non-doable because you can have a container, let the water flow to the container. You know the volume of the container. Then if you count the second, how many times to how long it to fill the container? Did you get the flow rate basically? Volume per time, right? So flow rate. Flow rate divided by cross-section area.
We're using Bernoulli equation from chapter 7. We'll have to incorporate head loss. And then we'll also have to incorporate HOP in it too, just because it won't be from chapter 4.
You can have the equation, write it down. Okay. So basically, when you design an experiment, you need to know every terms, either from experiment or from the given value. Okay. So to me,
I got you.
Yeah, you can actually measure this by just looking at the pressure differences. For example, you can set the things equal to 0. Okay. So yeah, maybe that's a little bit difficult to measure. You probably need to, it's not, Bernoulli velocity is the same, right? For a two portion of pipe. Maybe you can set the elevation the same. Basically, you can actually calculate the head loss based on the pressure readings if you have a pressure gauge. Then you can use this equation to theoretically calculate the HL. Okay, based on the, then it's a verification. You measure the HL based on the pressure differences. Then you use frictional head loss to calculate the loss. Okay, that's the two different ways to verify the head loss then. Okay. So or you can use the fiction this equation to calculate the head loss. Then place into your equation here to see, hey, my P1 minus P2.
Okay, so we could do the head loss and then put it in a Bernoulli.
Yeah, that's why you get the the head loss from one equation, then you have to verify it from the other equation. Okay, something like that. This is just to give you an example. I don't want you to do this. You know, this is probably, you still need pressure measurements to do that. Maybe if you don't have a pressure gauge, maybe you do. You know, but that's, you know, also I give it, I almost give it to you. So maybe don't do what I have already tell you. Okay, so but just an example. This is so purposeful example here. I just want to tell you, when you design experiment, you always can design something simple, easy to measure. Okay. So you really don't need to. And also, for example, pressure. Hey, if I really don't want to measure pressure, I cannot assume some value. Okay, maybe I can, because I know atmospheric pressure is 0. Maybe that one is slightly above atmospheric pressure. Let's assume something. As long as you said in the video, I know you don't have the measurement, but you say, hey, if that's what I assume, if that's reasonable, if it's a reasonable assumption, I take it. Okay, that's the value. So we can just treat it as the value you get or measured. Okay, then you do some calculation based on this. Then you can use another equation to verify it. Okay, so that I accept that too, as long as you say it clearly, logically in the video that I treat this as a measured value, but I don't have equipment. But I think reasonably this should be some certain value. That's fine with me too. Okay, I want to show the process. Yeah, the process, how you relate the reality with equations. Okay, how you verify it. That's a purpose of. That's similar to what you do in your final exam. In the text, also the same thing. Basically, you relate a physical phenomena, physical case, physical application. You relate that to an equation and solve it. See, that process is similar. Okay, that's why I kind of like you guys to do experiment, try to design experiment. Okay.
I'm sorry, can we get back to reviewing the final? So we only got 15 minutes left.
Yeah. I can, if you can stay here, I can extend for a couple of 10 minutes or something like that. Should be okay. Okay, I think that's all the contents here. Nothing more, just like this. Okay. Maybe 6 or 7 equations, 5 equations you probably need to memorize. You don't, if you haven't memorized yet. Okay, really not much. Okay, so again, my suggestion is you see a physical problem, see a problem statement related to a equation you're gonna use. That's exactly the key point. That's the key of the problem solving skill. Okay, so you just need to relate a physical problem into a equation. Okay, find the equation to represent it, and then you can solve that unknown in that equation. Okay. Let me give you some examples. I think it's maybe beneficial. I think we see. Let's go backward. Okay, chapter 7 and 10. Okay, chapter 7. I think we did an example for the pipe calculation, including all the losses, right? Let's look at that equation, the example. What is the example number? Example 7. Oh no, not 7, 10. No wonder. Okay, I want to talk a little bit about the 7.10. That's extremely important. Okay, 7.10, we did it, right? We use the Bernoulli equation between 1 and 2 surfaces, and we needed to find all the losses in there. Okay, but for the frictional head loss is easy. You can use a Moody diagram, find the F. I already talked about it in the class. The minor losses, I wanna make you practice one more time to find those cases. You need to know how to find those cases. Do you have that table 10.3 in your 10.5 in your phone? I think I sent it to you, did I? Turn on your phone. Let's see if you know how to use it. Okay, yeah, I sent it to you. This is 10.5 for the minor loss if coefficient case. Okay, can you take a look? Look at the example 10.7. There are 4 minor losses in there. Okay, the 3 minor losses in there. You have 2 bands. Yeah, there are 2 bands. I think there are 2 bands there. Okay, 2 of them. So can you find the K minor loss coefficient to me? Don't look at the example, just look at the table. It gives you R over D equals to 2. What is the K? The 2 bends in the pipe.
90-degree smooth bend.
Yes, it is a 90-degree smooth bend.
0.19.
Yeah, everybody know how to do that for this case, and there are 2 of them. So the K from the 2 bends will be 0.38. Everybody good with that? Are you reading the table? Because it really dictated by the turn, how sharp the turn is. The R over D, R is the radius of the turn, D is the diameter of the pipe. So it really dictated by how sharp the turn is. The sharper it goes, the bigger the K is, the more losses it has. Does that make sense to you, everybody? It's a shift, the sharper turn. It gives you more losses, right? Everybody? Is that common sense? Okay, because you directly hitting it, you suddenly turn, so there's a lot of turbulence in the corner. So okay, so more gradual change. The smaller R over D is, the smaller the K is. Smaller K means smaller loss. Okay, this is easy. How about there's an entrance? It's a 90-degree sharp entrance. Okay, what is the K for the entrance? Can you find it for me? From this table. What is the entrance K? Come on, there's no entrance in the table. So which one we use to represent the entrance? We use the first one. Okay. Does the first one look like an entrance? Oh, first one it is. It says entrance, pipe entrance. Okay. So find the K for me. It didn't say. I think it said R over D. It also requires a R over D, right? So it's a sharp entrance. So R over D equals 0. It's a sudden, you know, it's not gradual change. So what is the K entrance?
0.5.
0.5.
Said R over D equals 0.
Is that right? Sharp entrance, that means. There's no gradual change, no turns in the entrance, just a 90-degree sharp entrance. Okay.
Yeah.
So that if it's a sharp entrance 90-degree, then it will be 0.5. If it give you an R over D value, it means it's a gradually change the entrance. Then you have a smaller case for that. Okay. Okay. Entrance. The next one is exit. There's totally no exit in the table. Okay. Think about what we're gonna use as an exit. Well, we do have a contraction and the expansion,
Okay.
which
Reducer, use a reducer.
you mean contraction as exit? Your exit is this. Your pipe exit is kind of like this to a reservoir, to a tank, right? This is the exit, right? So which one is more close to this exit situation?
Being expansion with 0.
That's right. Exit, you use expansion. Okay. When it expanded to the infinitely large, you know, see, expanded bigger, right? But you actually, when you exited to a tank, you expanded to infinitely larger comparing to the pipe. So what is D1 over D2 if you become an exit? You see, D1 is the pipe before the expansion, pipe diameter before the expansion, then the D2 is the pipe diameter after the expansion. So if it's exit, what is the D1 over D2?
0.
It's 0. So your D1 divided by infinitely large, so it becomes 0. So if it's 0, what is the K exit?
1.
It's 1.0, right? Okay. There's also an angle. It's a transition angle, but when it goes to infinitely large D2, then of course it's 180-degree transition angle. So it's 1.00 for the K. Okay. So I guess this is the one thing I want to show you how to read those tables. Is that clear, everybody? So in the table, you also has a contraction, expansion. Both of them decided by the D ratios as well as the transition angle. I think it's clearly drawn on the diagrams. You should be able to find the case, okay, for these two cases. 90-degree middle band, there's a vein there for the 90-degree sudden change. Sudden change is terrible, so they put the veins inside the turn, so make it a little bit smoother, okay? Without vein, it don't even give you the value. It's pretty bad. Without vein, just like R over D equals to what? Equal to 0 for the smooth band, right? So with the vein will be 1.1 for the K, okay, for those situations. And the smooth band, we already used it based on the R over D, okay? And down there, there's also valves, gate valves, and angle valve, gate, global valve, many of them. And the gate valve depend on the open or half open. They have a different case. Also T's, elbows, two types of elbow is provided, 90-degree and the 45-degree elbow. Okay, so I guess that's the thing I want to emphasize on how to use those table. Mood diagram, I assume everybody knows. Okay, it's kind of straightforward. I didn't include those complicated problems for using Moody diagram, so for the sake of this class, but I think the one I introduced is pretty straightforward based on the Reynolds number and based on the surface roughness. Okay, that's chapter 7 and 10. I guess.
So for problems like that, it's probably good to just, as soon as you see it, write down all the pumps, all the openings, all the reducers and everything, so you can have it all ready to solve or ready to use the table.
Yeah, I think that's, you see, that's the equation you are going to use, 7 and 10. It's the energy equation, right? So many of the situation for the chapter 10 problem, chapter 7 problem, you're going to use these equations. But for comprehensive exam like this equation have a lot of letters. Some of the letters is also unknowns. So it's not just one unknown. You have 2 unknowns, 3 unknowns in this equation possibly. Okay, then we use some other equations from other chapters. For example, if HL, then we can use these 2 equations from chapter 10 to calculate. Okay, for the velocity, maybe we can use chapter 5, you know, for conservation mass to calculate it. Okay, pressure, maybe use some other principle to calculate it. Okay, so-called comprehensive problem basically is just in the equation, in the main equation, there are multiple unknowns. Okay, for the straightforward questions, just like give you the equation, use this equation, just only one unknown in that equation. Everything else you know. So that's a straightforward directly calculation. Use that equation. So-called comprehensive problem is for this equation, you have 3 unknowns there. Okay, basically you cannot directly find out anything. 3 unknowns, none of them you can be calculated. So you have to use other principles. Okay, other chapters equations to find out those unknown individually. At the end, you have only one unknown, then you can solve it. Does that make sense?
Dr. Zhang?
Yeah.
Is there any significance for the theta values they chose to include in the K-value chart? Like the 20 degrees or the 60 degrees for the contraction and the expansion?
I don't know what to say. This I just will, if it's 20 degree, I will tell you it's 20-degree problem. So you can just directly find the K. Okay, if I but these are for the applications. Usually, commonly people use these 2 angles for the expansion, for example. Okay, so if you have a complete table, you have a 20 degree, 30 degree, 45 degree, all the angles, they give you a case. But for the textbook, maybe that K can be only K can be a whole handbook for case for different detailed information. But for our textbook, now it just give you a couple information for you to use to practice. Okay, so okay, this is 7, and let's go backward. Maybe 6. Chapter 6, momentum is sometimes people complain as a difficult chapters because they didn't follow, usually they don't follow the procedure. We solve problems. So let me give you an example, maybe not the whole example. I just give you some direction. I think that's one of the homework problem. Okay, 6.13. Let me show you how to solve this type of momentum problem. It's slightly different comparing to the example problem. So it's a tank. There's velocity coming out from the tank, right? Now it's pretty easy for you for this type of problem. So there's the velocity coming out. Let's say this water stream shoot on a plate. Okay, the kids sometimes in the backyard play this game. They shoot the water from the water hose, hiding a plate holding it. You will feel a lot of force. The water goes up and down, right? But it will apply a force basically to the plate here. Okay, you have to use force to hold it. Does that make sense? That's a common situation. So it's possible to put it in the conservation mass topic, right? So if situation like this, how much force needed to hold this? This is not exactly the problem as 6.13, but I think that's the same. The problem asks you to calculate the velocity, but I ask you to calculate how much force you will need to hold it. So let's say this height is certain height. Let's 10, tank is 10 feet. You don't like feet, right? Let's say 5 meters. Okay, so you shoot it out with velocity. Assume that there's no loss. So the water stream is the same diameter. Okay, I might give you a diameter, whatever diameter, let's say 5 centimeters. That's too big. 2 centimeters. Okay. So what's the force needed to hold this plate, hold this shell in place? Okay, how do you do this? This is conservation momentum, right? So which one is the target control volume? Okay, I think the control volume is this water stream. Okay, for the plate, it's easy. You have a force applied to it, you need a force to hold it. Not much. Okay, then the question is, what is this force, right? Basically, you want to calculate this force. But actually, the force is coming from the water stream. So you need to draw the free body diagram for the water stream. Okay, free body diagram. Okay, so you have a force coming from the shell. That's action reaction, that's same force. Actually, that's a force you want to calculate, right? Okay, or anything else? Pressure force. I think there's no pressure force here. P is 0, atmospheric pressure. So PA is 0. So you don't want to worry about the pressure force. So that's only one force is the force required to hold it. Okay, so momentum diagram. This can be treated as a 1D problem. You know what? Because to go up and down, they canceled out, right? So you can only consider the x direction. So the momentum going in and the momentum go out is 0 because it's blocked here. That makes sense? Your momentum is go up and down, but it's in a y direction. Okay, y direction will be canceled. You don't need a force in the y direction. Your force is the x direction in the free body FBD, right? So your equation here is negative F, which is the force required to hold it, become momentum. Momentum out minus momentum in, right? 0 minus momentum in, mass flow rate times velocity. Out minus in. There's no out in x direction. This is x direction momentum. You're calculate x direction force. So basically, the force required to hold it is basically simple like this. Negative m dot v. Do you understand this? Any question here? Did I go too fast? Okay, separately look at the problem as force diagram and the momentum diagram. Force diagram, look at it, and nothing except the force required to hold it. Let's neglect the weight. Okay, so that's only force from the surface applied to it. In the injection, because it's open to atmosphere, no pressure force. That's it. So that's only one force. And since I placed the force sign in this direction, I put the negative sign here, negative Fx. And for the momentum, for this water stream, you only have one momentum in. Okay, momentum out is going up and down. So in the x direction, there's no momentum out because it's blocked. Okay, that makes sense? Okay, so in x direction, equation will be extremely simple. One force terms and the one momentum terms. Be careful, momentum out minus momentum in. Okay, momentum out is 0 and the momentum in is positive. So this is 0 minus m dot v. Okay, so can you calculate the m dot v? This is uniform velocity problem. M dot is equal to rho VA times V. Basically, that's it. Velocity you can calculate from the Bernoulli, right? The tank is h 5 meter height. Can you calculate the velocity at that moment? What is the velocity? Anybody? Can you remember that? What is the outlet velocity? Anybody? Hey, come on, communicate with me. Give me an expression for outlet velocity from the tank.
For velocity?
Yeah, it's a tank. You have open to atmosphere. You shoot it out the water, right? What is the outlet velocity?
I mean, from this equation, it's force over mass flow rate.
No. You need to calculate the average outlet velocity to calculate force, right? Force is your unknown in this equation, right? Is that right, Josh? So you need to find a way to calculate the velocity outlet in order to calculate the force. Is that right, everybody? You forgot how to calculate the outlet velocity of the tank when the tank is going out?
You use Bernoulli on it?
Yes, use Bernoulli. Can you memorize that outlet velocity? V equal to square root of what?
2gh.
That's right. Come on, you can memorize it, right? Yeah. Do you know h here?
$15.
I said 15. I said 5. Okay, it doesn't matter. I make up the number. Anyway.
Okay.
Okay, so you can calculate the outlet velocity, right? Do you? At that particular moment, we only talk about that moment, right? It changes. You know, it changes from chapter 5. We know it gradually changes, but at this particular moment, your outlet velocity can be calculated. Do you agree? Huh? Everybody? Can you calculate the mass flow rate then? Can you? Rho VAV, right? Mass flow rate is just rho VA. Okay. Density, velocity, you calculate it here. Area, the diameter of this jet is 2 centimeters. Can you calculate the area? Anyway, I still don't see response from it. Is that clear enough?
You said rho VAV?
Is that mass flow rate rho VA?
Yeah, what was the extra V?
It's for momentum. Eventually you need the time of V.
Oh.
Is that right? If you get the velocity, can you find the momentum? That's it. Then you can calculate the force required to hold this jet. Okay. Okay. So follow those equations. The equation you write down, when I circle those equations, I write down. If it's correct, then you can just follow that. You know, you want to calculate the Fx, You just need to find a way to find out the mass flow rate times velocity. Mass flow rate, think about how do you calculate velocity. Okay, mass flow rate is from the velocity. Okay, you need to use other weapons like Bernoulli, whatever, conservation mass, pick the appropriate one to find the other values like velocity, and then solve the problem. Okay, this is another example for momentum. Okay, any questions? Crystal clear to everybody here? Okay, I see Devin nodding. You're good, right? Okay. How about Dylan? Any questions?
I'm good. You answered all mine.
Okay, good. Josh is good, right? Okay. Patrick, Daniel, okay. How many we have? Okay, several of you here. Okay, so this is another example. This is actually a homework problem, so I can show. I think that's also important. Then what? Chapter 4, Bernoulli, we talked too much about it. It's actually Bernoulli now become easy equation. I don't think a lot of problem you can use Bernoulli. You have more complete equation here. So to replace Bernoulli can include most of the other factors. Okay, hydrostatic. Okay, again as we reviewed here. Okay, hydrostatic have a couple important content, 4 important contents here. Okay, we have a bunch of example homework problems in quizzes problem for those. Okay, I think again you need to memorize those equations, not many. Okay, 2 or 3 equations maybe, or maybe just one equation is a little bit difficult to memorize. Everything, all the other equations pretty straightforward. Maybe 2, right? This equation and this equation. Okay, on your notes, I guess. Okay. I guess I'm out of time, really out of time. It's 11 almost. So I guess that's it for today. Hopefully this is really beneficial for your preparation for Thursday's test. Okay, I hope you didn't waste the 1.5 hours here. Okay, so learn something and we'll help you.
I don't feel like there was a lot of questions. I don't feel like there was a lot of question and answer on the actual final part.
Well, final now, let's say, I need to say something about final, since you remind me. 4 problems for the final, and the time is 8 o'clock, okay, 8 to 10 in Fresh 101, okay, and the social distancing guidance need to be followed, so everybody need to wear a mask and or maybe face cover, whatever. So we need to follow the guidance. And let me see what else. Yeah, be here maybe 5 minutes earlier before the test. We can make sure everything is good, then we start the test. Okay.
One final question. Is there a place, let's say that you found when you were a student that we can look that ties everything together, that has a lot of questions, like you said, you're not going to do any tension problem or surface tension, but you're going to add it to another one? Yeah, I didn't see, there wasn't a lot of that in our homework that tied it.
No, it's not. No, let's do this. You have some misunderstanding here. Exam is not homework problems. Okay, exam has to be comprehensive, final exam. Okay, so it will be a level up than the homework problem. Homework problem for each chapter has a separate problem. It cannot connect many different chapters, at least unintentionally. But in the exam, we have to combine all the knowledge together, be a comprehensive exam.
But I mean, obviously, before I do something, I would like to practice that way first, not just be hit with.
My suggestion is you practice those homework problem, because that's the problem designed for each chapter for test your concept. If you're good with those tests concepts, I think it will be good to combine. Just like I said, you combine those knowledge is not really difficult, because when you look at the equation like this, what do you mean by comprehensive? Hold on. What do you mean by comprehensive? Listen carefully. Comprehensive means you have multiple unknowns in a equation. Okay, that's the true meaning of a comprehensive problem. Okay, if you have one unknown in that equation, that's not qualified for comprehensive. Basically, you just calculate that unknown using that equation with the knowledge of everything else, which is given. But if you have 2 unknowns in this equation, then you cannot solve these 2 unknowns, right? You have to find the one unknown first before you solve the other unknown. to find that one unknown first, you have to use another equation to find that one unknown. Then you combine the two equations. Then you become a comprehensive problem. You apply the two principles in this problem. Okay, so that's what I said, the comprehensive problem. Basically, it's easy. So basically, you look at this. If you have two unknowns, I will circle the two unknowns in this equation. Okay, so you use a conservation mass to find this unknown. So if you know how to do conservation mass problem, just like what you practice in chapter 5, then you should be able to find this velocity using conservation mass. Then
yeah, that's
substitute
actually,
to
that one. That's probably the easiest one to tie conservation of mass and Bernoulli and all that together. But there's some that
it's
that
all
maybe
all like that.
That I haven't seen tied together before is what I'm trying to ask. That maybe somewhere I can get a better idea of what it might be.
It's not tied together. Why you feel it's tied together? You just say,
I mean,
hey, I don't know the pressure
together,
too.
But
well,
like if I don't know,
too.
When I have to use conservation of mass to solve for V to plug in, you know, something like that.
I think that some of the later chapter homework problem, basically it is comprehensive already, because the later chapter, they use the previous chapter's knowledge already. So if you want to see more similar problem, like more level of comprehensive, but it's not really, I don't know how comparable to the final exam problem, but it's already comprehensive because it uses, suppose you know the knowledge of Bernoulli, you know the knowledge of the conservation mass. So it asks you to calculate the velocity from conservation mass. It asks you to calculate the pressure from other equations, something like that already. So that's already a comprehensive problem. So in the exam, there's similar faction to that. If you want to see, I think that's probably a good idea. You look at the later chapters problem. That's actually more comprehensive than early chapters problem. Okay, so then I think a lot of chapter 10's problem is very comprehensive. I don't know if you do those problems as assigned. Some of them you have to go through 3 steps to calculate the pressure. So that 3 steps basically use other principles already. So I think it's very comprehensive. So I guess that's the question you probably ask. You want to try to do those later chapters problems, to have a better feeling of this. Right, Josh? Does that make sense?
Yeah, thank you.
Yeah, you're welcome.
Dr.
Any other
Lane,
questions?
Yeah, there was a Euler, Euler equation problem that you gave like a little bit earlier in the year. Could I email it to you since you're out of time? I just couldn't get like one little answer at the end.
Yeah, sure. You just email it to me. I'll talk about it to you. Yeah,
Gotcha.
You could text me or email me. Send me the picture or which whatever your writing is or whatever problem is. I'll talk about it. No problem.
Cool. Thank you.
Yeah, you're welcome. Okay, I guess that's it for today. Okay, good luck Thursday. See you on Thursday, and good luck on all the other finals too.
Thank you.
You're welcome.